Hello, welcome to the final episode of Stats with Matt. I appreciate you going on this magical statistical journey with me. All good things have to come to an end, or good things have to come to an end. Things are not beautiful if they last forever, and it is better to have loved and lost than to have never loved at all. I'm not introducing any new material today. What I am doing is hoping to review a bit for the final exam. And I say that with some quotation marks there. I have decided that, look, I have very little interest in, policing the student code of conduct. I have very little interest in putting a ton of onerous requirements on my students at this point of the semester. What is important to me is that you demonstrate competency with the material and the hypothesis tests that we have gone over in the second half of this semester. And to that end, that is what the final exam is. It's one final 75-point assignment to earn you the points that the class's syllabus dictates you need to earn, and gives you a chance to show me that you can carry out all of the statistical hypothesis tests that we have spent time on over the past 7 weeks, okay? So my goal today is to demonstrate the skills you need for this final assignment and to review the steps of arriving at the right observed value, because that's the key. That's the thing that is where the majority of your points will be earned or lost over this final assignment. So let's get into it. I am requiring you one last time to demonstrate that you can carry out these hypothesis tests from step 1 to step 6 of all of the following hypothesis tests. You will need to remember how to do a t-test with an equal sample size, right? 2 means t-test with an equal sample size. You will need to do a 2 means t-test with an unequal sample size across those 2 means. You will need to do an ANOVA problem. You will need to do a Chisquare problem. You will need to carry out bivariate correlation by hand. You will need to carry out bivariate regression by hand, and you will need to carry out, You will need to interpret multivariate regression tables that are presented to you, and to be able to interpret the interval level independent variables, categorical independent variables, R squared, and the y-intercept of a model. Nothing we haven't done before, no surprises, no tricks. Things is going to be presented to you the way that you're familiar with it being presented to you. And I want to see that you can do the steps in the correct order. And I want to see that you can solve these problems correctly. Okay. So to that end, I want to go through each of these methods, each of these hypothesis tests, and go over especially step 5, which is where you're actually doing the math and crunching the numbers. When you sit down to do the final exam, there is no time limit, so long as it is turned in no later than the deadline that I have put out to you, which is April 29th at 12 p.m. I have to have a little time to grade the seniors, even though grading in this class is honestly a lot easier than it is for any of my other classes. You are entitled to make use of the lecture videos and the stats packet. Like I said, I have no interest in putting onerous requirements on you. I want you to demonstrate that you have learned this material. If you can do that, and you can do that honestly, then all the materials that we've gone over are available to you. Okay, so let's go through what is required of each one of these tests. If we are doing a t-test, you'll remember that's a difference in means. You're given 2 sample means. And how do we order them? That's one of the ways in which this can go wrong. You may remember, if you remember all the way back to about over a month ago, how do we organize our means for the t-test? Well, it comes down to whether or not you have a directional hypothesis. If you are being asked to conduct a one-tailed t-test with an expectation that one sample means value will be greater than the other sample means value, you should make the larger sample mean x1, make the smaller sample mean x2, and you need to be looking for a critical t that is positive, okay? If the one-tailed test is going in the other direction, there, I need to reverse this. Make the smaller sample mean x1, make the larger sample mean x2, and now I need to be looking for a critical t that is negative, okay? And your value, like for a greater than one-tailed test, I need to calculate an observed t that is greater than the positive version of that critical t. And it's the inverse for a one-tailed test hypothesizing a less than relationship. If you have a two-tailed test, doesn't matter. Put them in whatever order you want, and you have to be looking for a critical, or you need to understand that the critical t is then the positive or the negative version of what you look up on that table. Nothing too complicated there. You just have to take steps to organize things appropriately. Okay, so when it comes to doing step 5 for a t-test with equal ends, you have to first calculate an estimate of the difference between the standard errors. That is represented by S of x bar 1 minus x bar 2, which is calculated by taking the variance of the first sample. See how that's S squared, the variance. So if you're given standard deviation, make sure you square it to get to the variance, divided by the first sample size plus the second variance, the variance of the second sample, divided by its sample size. And here, N1 and N2 are understood to be the same number. You do that, take the square root, and that becomes the denominator of the problem here. You can see that S of x bar 1 minus x bar 2 is calculated in this manner. You plop that right in the denominator here, and that becomes the denominator of your t-test, where t is equal to the first sample mean minus the second sample mean, or to put it in the terms that you see in this formula, x bar 1 minus x bar 2. Nothing too complicated there. If our ends are unequal, it gets a little bit more complicated. So with unequal ends, we use the same logic, except before we use the calculate the difference in the standard errors, we're going to have to weight it first. So if we follow the flow chart here, we start with 1, go to 2, and then go to 3. So the first step is to calculate S squared P, where we are going to weight the estimate of the standard error, the pooled estimate of the standard error. We're going to weight that to assign more value and more explanatory power to the sample size that is larger, because the variance of the sample size that's larger is known to be more accurate in almost all circumstances. So S squared P is calculated as the first sample size minus 1 times the first variance plus the second sample size minus 1 times the second variance, divided by N1 minus 1 plus N2 minus 1. A lot of that stuff is actually stuff you'll already have in steps 1, where you state what you know, and step 4, where you have to calculate your degrees of freedom in order to get that critical value in the first place. So I do step 1 here to calculate S squared P. I then move to step 2, which is calculating S of x bar 1 minus x bar 2, where I need that estimate of S squared P in order to get the right answer here. So S squared P over N1 plus S squared P over N2, and then I take the square root of that. In this case, S squared P for both of these terms here is the same number, but N1 and N2 are no longer the same number. Makes sense, right? Here, if it's unequal ends, we have to account for the fact that the two ends are going to be different. And then that calculation for S of x bar 1 minus x bar 2 goes right in the denominator, where we're still taking x bar 1 minus x bar 2 to get our t estimate. So take care to figure out if this is a one-tailed test or a two-tailed test. Arrange your x bar 1 and x bar 2 appropriately, and do the math in order and check your math. Because I feel like I've said this a lot, but it's true. Every single one of us is capable of making a careless math error. Every single one of us. There isn't a single person that's not capable of making a careless mistake. If you want an A in this class, you'll check your work, okay? All right, moving on to ANOVA, right? This was where we now had sample means across 3 or more groups, okay? So we could not use the logic of the formula of the t-test, but we could kind of use the logic here. And with ANOVA, we had at least 3 sample means to go along with a grand mean. Okay, so the group means referred to the sample mean for each group. The grand mean refers to the mean for all groups, for all observations, regardless of the group. So when it comes time to actually conduct an ANOVA, I suggest splitting step 5 into the following 7 steps. First, calculate those means. And you should already have that because that's part of stating what I know in step 1. If I have 3 groups, I need X bar 1, X bar 2, X bar 3, and X bar total. If I have 4 groups, fine, just throw an X bar 4 in there and make sure you have X bar total as well. Step 2, I will need to calculate the sum of squares within the group. It's the total sum of squared variation that is occurring within the groups. And in order for ANOVA to reject the null hypothesis, we generally want to find more variation between the groups and less variation within the groups. Because if it's all happening within the group is less important. The group is not really mattering there. So we do that using the group mean. The sum of squares within is the summation of xik, where xik is each observation minus its group mean squared and then summed. So for each observation, we subtract its group mean from it, we then square it, and then we sum it, and then sum that for all groups that you have within the problem. For step 5.3, similar logic here, except we're dealing with the grand mean. So for each grand mean, that's nk, I will then, that's x bar k, I will subtract from that group mean the grand mean. I will then square that and multiply it by the size of the group. And I will have to sum that 3 times if I have 3 groups. If I have 4 groups, I'll have to sum it 4 times. And once I've done that, I've done most of the heavy lifting here. So steps 5.4, calculate your degrees of freedom both within the groups and between the groups, where df between is equal to k minus 1, where k is the number of groups. df within is n minus k, where n is the total sample size, and k is, once again, the number of groups. And then I can use that to move to step 5.5, where I'm calculating mean squares within by taking the sum of squares within and dividing it by the degrees of freedom within. Not too much more now. Calculate the mean squares between by taking the sum of squares between the groups and dividing it by the degrees of freedom between the groups. And then finally, calculate f, mean squares between divided by mean squares within. Do not forget that the last thing you typically have to do with an ANOVA problem is to report upon the strength of the association regardless of whether it was significant or not. And we do that using elephant squared or eta squared. Use the eta squared, the thing that looks like a big elephant trunk. You will report that as part of your ANOVA interpretation. Make sense? I sure hope so. Okay, put another way, f equaling mean squares between over mean squares within is essentially the ratio of the variance between to the variance within. If we have a very large f, chances are we will reject the null hypothesis. If we have a very small observed F, we will more likely than not fail to reject the null hypothesis. Now, moving on to chi-square. Chi-square is used when we want to test for an association, at a bivariate association between two categorical variables. So we used religion and God, what was it? I'm drawing a blank here. Religious affiliation and political preference, right? We couldn't calculate a mean there. Therefore, all we could go by was what are the percentages? What do we observe? What do we expect to observe if there was no relationship? So chi-square is the summation of each cell's observed frequency minus the expected frequency squared and then divided by the frequency expected. So when you read this table, F observed, that's what you actually see in the cell. Frequency expected, that's what you would get if the total percentage was the same as the group percentage, right? So if you remember going through the example we did as a class, whatever percentage of people are Republicans regardless of religion, that's the percentage I'd want to see being Republican within the Catholic group, within the Protestant group, within the Jewish group, whatever. I would need to see that mirrored in order for there to be no relationship between the two variables. Similar to ANOVA, chi-square is no-tailed. If this number is very large, chances are we will reject the null hypothesis. If chi-square is calculated as being very small, chances are we will fail to reject the null hypothesis. Moving on to Pearsons R, this is when we got to what I consider to be the fun stuff. I don't consider ANOVA to be fun, but I do consider Pearsons R and regression to be an absolute blast, and I am not kidding about that. Like, I legitimately am excited by this kind of stuff. There, I need to calculate a Pearson's product movement coefficient. That refers, the correlation coefficient refers to whether or not there's a significant relationship between two interval level variables. I want to understand the strength of the association there. Not the magnitude of the effect, but the strength of the association. So what we did here, remember to create a table where you have X and Y values listed in the first two columns of your table, and then calculate a column for XY, where X is multiplied by Y, a column for X squared, and a column for Y squared. Then you will want the summation of X, the summation of Y, the summation of XY, the summation of X squared, and the summation of Y squared. Finally, sum all those columns and complete the formula, where R equals N times the summation of XY minus the summation of X times the summation of Y. Pay very careful attention to your order operations here. Divided by the square root of N, N times the square root of X minus the square root of X, or minus the summation of X, pardon me, squared, times N times the summation of Y squared minus the summation of Y, pause, squared. R, you will remember, can only ever be between -1 as a minimum and +1 as a maximum. The closer it is to these extremes, the stronger the relationship is. The closer it is to 0, the weaker the relationship is. A negative R means that as values of X increase, values of Y will decrease. A positive value for R indicates that as values of X increase, values of Y also increase. Now, as for what we'd want to do if we had to report on the average effect of an increase in X, regression by hand. Two formulas. You will remember that our simple bivariate regression equation is y equals bx plus a plus e, but e is not usually interpreted or calculated. B is the slope coefficient, or it is the effect of x on y, and a is the y-intercept, which functionally is the value of y when all x's in a multivariate equation equal 0. So I will first want to create that same table that we had in the previous problem for the summation. Looks like I'm going to need the summation of x, the summation of y, the summation of xy, and the summation of x squared. There's nothing wrong with calculating the summation of y squared, but it's just extra work and you wouldn't need it for this particular problem. I then run through the formula for b, where I do n times the summation of xy minus the summation of x times the summation of y divided by n times the summation of x squared minus the summation of x squared. And that value is understood to be a 1 unit increase in x is associated with a b unit change in y. Positive values for b indicate a positive relationship. Negative values for b indicate a negative relationship. It's no more complicated than the product movement coefficient. You're just getting extra and more and better information. Once I have b, I can calculate my y-intercept, where a is equal to the summation of y minus that slope coefficient, or b, times the summation of x divided by the sample size of n. So b is the change in y given a 1 unit change in x, or increase in x, I should say. And a is the value of y, assuming that x equals 0. And then, if we have to do a multivariate interpretation, no problem. All that happens to the formula is it becomes y equals b1 x1 plus b2 x2 plus b3 x3 plus bn xn plus a plus e. So if I have an interval level variable as an independent variable, a 1 unit increase in x is associated with a b unit change in y, net of other effects. Dr. Schoen, do I have to say net of other effects? Yes, you do. If I have a categorical variable, the coefficient labeled as b is understood to be the effect of being in that group, coded as 1, as compared to the reference group, coded as 0. So your interpretation would then follow the following format. Group 1's values are b units different from group 0, net of other effects. If I have a simple situation, a simple dummy variable where those with a college degree are coded as 1 and those without a college degree are coded as 0, then in that situation, whatever my coefficient is, it's the effect of having a college degree as compared to those who do not have a college degree. Group 1 always compared to group 0. As for my y-intercept, which is labeled as the constant in the regression output you're used to seeing through Stata, the y-intercept is the value of y when all x's equal 0. So to take the example of number of children here, right, the value for y that you saw there, it's the number of children people can be expecting to have when all x's you have included are set to equal 0. In the case of a multivariate equation, you have to say all the variables that are equaling 0. And then finally, the very last thing you're responsible for, r squared. R squared is the total percentage of the variation that you have explained, the variation in y, the dependent variable that you have explained through the inclusion of these x's, or these independent variables, because that's what you're trying to do. Like, you have all this variation in the dependent variable. What you're trying to do with each x, or each independent variable you include, is to predict those values. You're trying to predict what happens to y given values of x. The greater that r squared is, the more variation you are capturing, and the better the model fit is for the data. So if r squared equals 0.3975, then I would say 39.75% of all variation in the dependent variable is explained by the inclusion of my series of independent variables. And that is it. Can you believe you're almost done? While I will not be making any more videos, I personally remain available. I'm more than happy to get on the phone with you. I'm more than happy to get on Skype with you, or to answer emails you might have about any of these issues here. By the time you watch this video, you will have access to the final exam. Get it in on time, take care with it, and I have faith you're all going to be just fine. Thank you very much for working through this with me. It has been my pleasure to be your professor this semester, and to those of you that are graduating, I say congratulations, and I say that you are always welcome to keep me in mind if you feel that I can be a professional resource to you. To those of you that are coming back to Albion next year, I really look forward to seeing you again and catching up with you. Take care of yourselves. Good luck.